Hey, if you're watching this, you're watching the first video of the cannoning series. This is an added bit of audio to the start of the one I had already previously uploaded, which was behind a paywall because of Minecraft EULA, Mojang's new EULA, which was updated day after I posted the first video. I cannot offer paid videos on my YouTube channel. So this is now free. I fixed a couple things that were mistakes in the first video with rendering errors right here. So that's all I've got. Hope you guys enjoy. Hey folks, thanks for checking out this first episode of the Cannoning Essentials videos. This one we're just going to talk about, I think, basic TNT movement and what are important assumptions you need to make when working with cannons. There'll be like a history thing too, but I do want to get some of this like basic movement stuff down first. So let's get started. I am on a basic 1.7 server. This means there are no TNT patches. So TNT moves just like it does in vanilla Minecraft. It jumps around and stuff. And the reason for that is I want to go back in time to when cannons were just starting out and stuff like that. And it's kind of to emulate original Minecraft servers and stuff, or like single player without having all the crazy patches. So this is just like a basic like TNT cannon that people made like when Minecraft was new. I can't give it a date, 2011, 2012, whatever Minecraft became a thing. So let's give it a shot. And you see how the TNT jumps around with these tracers? Just like that. So it just shoots. You can see it's kind of like an arc or whatever. So and that's with the slab. Similarly, if we do it with the ladder, it's going to follow a slightly different path. And that's because of exposure, which I'll get into in a second. See, that goes further up and farther in total. All right, let's take a look. So what I've gone ahead and done is I've done a whole bunch of testing here, as you can see, and I'll seriously talk about all of them in a bit. And I've used different things for exposure and stuff like that, which again, I might have said it in the previous clip. I'll talk about more of that soon. But a big thing we want to talk about is physics, and we want to talk about particle movement, and I don't want to say movement laws, but like movement equations and such. So for something like this, we have this power, and because this is raised up some, we're going to have two components of force. We're going to have something moving in the x direction, and we're going to have some moving in the y direction. So what you can do is you can create equations. For example, x naught is equal to x plus v naught t plus 1/2 at squared. And what that'll give you, if you have acceleration, velocity, and position, that'll give you a parabola, something that looks kind of like x squared plus 2x plus 1. It'll give you that sort of shape, and that relates velocity, position, and acceleration. So you do that for both the x component and the y component. And for most of our cases, you'll see that the x component, what's moving in the horizontal direction, so horizontally, that is a linear relationship. Whereas the things moving up and down, that is it's a parabolic relationship, a quadratic relationship, something similar to that, because of gravity, which is the whole reason why things go downwards like this. So we'll break that down. What I've done is I've shot this a whole bunch of times using different barrel things, and then in other spots different power. But for example here, we can clearly watch the parabola. Also keep in mind the TNT jumps, so inaccuracy. It goes up, and now it's going to start coming down because of gravity. However, it goes at the same rate sideways. So let me pull up some graphs. Now, something important we want to talk about here is we want to break the components up to learn some more things about cannoning. Because you see, this goes upwards and downwards, and we don't really want this. It is inaccurate, it causes lots of problems, and if we're doing advanced cannoning, we don't want upwards. We want straight and down. So let's go down a little bit. So these are the components, velocities, in terms of time. This is a function of x and y. So the x location gives us a y. That is very important. You need to understand that x and y. If you can imagine these x's here as t's, and that y, for example, as an x. Anyways, this is with time. This is super important. These are two different things. This is a linear relationship here. This is a straight line. And this corresponds to the x location. So what I did was for the specific times, so 1 full repeater, 2, 3, 4, 5, 6, 7. For full repeaters here, I plotted the x location, the horizontal location of the explosion, and the time. And it's a linear relationship. Now, the reason why this makes sense is because we give no acceleration. There's no acceleration on the the TNT as it's going straight. All acceleration is because of gravity. Gravity only goes downwards, which is this. So what this means is it's just going to go in a straight line horizontally. And you can see it grows linearly, which you can see by this line. Now we want to look at the y displacement with time. Keep in mind, this is not the graph of the actual movement. This is time, not x. So with no guider, that's an important word, it's going to go upward some and then downward some. And there's initial y velocity because just like this, we have a velocity here. Something similar, we have a velocity starting off right here, which is the angle it takes. But because of gravity, this, maybe not this specific one, but there is gravity, and it's going to pull it downwards. And eventually it's going to overcome and it's going to start going down forever. So these are two separated equations, but they're related to each other because of time. And I'll break into that some more. So because of these two equations, x of t and y of t, where t is time, x is the horizontal displacement, so this, and y is the vertical displacement, this, we have these curves. And depending on the exposure, we're going to have different values in terms of how far they go in one set of time. So for example, for the same set of time, we have this one and this one. This is for the slab, I believe, and this is for the ladder. The ladder gives more exposure, so not only does it go further in the x direction in a certain amount of time, it goes further in the y direction. So an assumption we can make now, this is important, is that the higher, like the greater the exposure we can get, the faster or further it's going to go in a unit of time. That is very important to remember. So we have the slab here, and there should be a block somewhere, but a full block is not very good, which we can see by this glass. So for example, this is glass for one set of time. For the same set of time, this is for a slab, full block, slab, and this is for a ladder. So we see the ladder's greatest, and it gives us the most in the y and the x direction. So to come back over here, I have here a ladder, so it's the greatest exposure, but we're going to get rid of all the y stuff. We're only going to worry about the x direction. So we have here a guider, and every cannon now uses that. Because when you're shooting a base and you want to shoot a wall, for example, let's say you're doing 100 walls. If we follow the pattern here, we're going to have a hole here, and then we're going to have a hole here, and then we're going to have a hole here, and then we're going to have a hole here, and then a hole here. And that's really troublesome to work for. It's not consistent at all. We have this arc path for the TNT, and it's just not a good thing with TNT cannons. So I'm going to go ahead and fire this. You can kind of follow the path this is going to take. Still TNT randomness, it jumps. You'll see it there too. Look at that. It still goes downwards, but it still goes sideways at the same rate. And you can see the Y location, another very, very important tidbit, the Y location for every given amount of time is exactly the same. The only thing now that's different, there's obviously errors, which I've talked about. For example, right here, this is an error because of TNT jumping. But for every given every given amount of time, the y displacement is now the same because there is no initial y velocity. If there's no initial y velocity, no matter what the linear relationship is, the vertical relationship is going to be the same. Now you can see the exposure now doesn't have much effect. The y exposure does not have any effect on the system. However, the ladder, the exposure is still important for the horizontal component. As we can see here, this right here is the slab, and this right here is the ladder. So the ladder goes further still, which is to be expected. So if you want to maximize your cannon, you want to use a ladder instead of a slab. Now let's break down the x of t and y of t some more. This is just the x versus y plot. So here is the graphical representation of the x versus y, which is what you see on that glass backboard with the wool and clay. Ignore this gray line for a second. I'll talk about that shortly. Blue is with the slab, and orange is with the ladder. So once again, I've put equations here. Ignore this one. You can see it's a perfect fit. This is for the slab. This is for the ladder. So it's a very close representations. Now we've gotten rid of one random element of randomness, which is y velocity. The reason why this arcs upwards then comes down. So gravity is still in effect. It's going to be whatever the same rate. There's air friction or something like that in Minecraft. Don't want to talk about that. There is acceleration here, and it's the same for both. So these are much more accurate, as you can see. This is an r² value. It means stuff. I'm not going to break into basic math stuff here. So false I am. So we could see here that it obviously everything pulls more to the right, further along the x-axis because of the ladder when that. So now we want to break it into the x of t and y of t for the ladder. And we'll talk about the slab in a second. So we can still see a linear relationship here, but when you compare right here, this is with no guider right here. You can still see there's an arc here, and we can see here that with the guider, there is no upwards, so it's going to go downwards in a quadratic relationship still. So, important note, this is because of the amount of power and the exposure. This is just because of gravity. And you can see I have these yellow dots on top. This is a slab. This means that no matter what type of cannon setup you have, for a given amount of time, it's always going to come down the same amount. With no y velocity, no initial y velocity, gravity is going to act the same for the unit of time, no matter what. That is why these values are the same. However, these gray dots, that represents the slab, blue represents the ladder. The ladder is always greater, so that's the important thing. Gravity is going to be the same. We really only want to focus on the x values, the horizontal values. And we want to use ladders or slabs or different barrel setups to maximize the x component. Because if we reduce or just ignore the y component by using a guider, it's always going to be the same. And we can kind of show that again here. This causes lots of random errors. Any sort of arc, no guider causes problems. We want to have a guider because this function right here is always going to be the same for the most part. And we can then solve that using this. So what I've done, because these are both functions of time, so in this case, x equals 13.417 times time plus a constant gives us this line. Here, the y displacement is equal to this value times time squared minus this, blah, blah, blah. That is acceleration, velocity, and whatever. We can then solve it for time, one of them. So let's say we take this x1. We can rewrite the whole thing, so now it's x minus 10 point blah, 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 divided by 13 gives us time. We can then plug this into this equation down here, and we will get this one here, which is interpolated actual movement. So rather than using, okay, so here's more math stuff. We have errors here, specifically looking at the blue and orange. So I have fit a curve to only the y or x components, then solved for them, plugged it back here. This is a very close approximation of how it's going to actually plot, but yeah. If you can kind of imagine this gray line here, it is rounding twice, if that makes sense. For this orange and blue line, I'm only rounding once. So you can see here, I've fit a curve to both of them in this case. So I'm rounding here, and then taking this rounded function, plugging it into this rounded function. So there's going to be more errors present here. I'd be interested if I could do like a confidence interval, 95% and whatever, and it would show like a range. But if you can imagine like a slightly wider line, you can see it would kind of include both of those. So it's a very close approximation considering the random jump in TNT and other little errors present. But what I've done now, back on track, this right here, this entire plot, what you see on that glass backboard is a function of x versus y. These two equations are functions of t versus the x or y displacement. I have then solved for time, put the two equations together, and I get an x versus y plot that actually deals with time. So to break into blah, 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 blah stuff, here's the solved like x equation. The variables don't match up. That's fine. But I've kind of reversed it. So this is time and this is x. I've then plugged it into the other x equation, excuse me, y equation. So normally there'd be a t here and a t here, which is this value. And we can then plot stuff. So I talked about how there's y acceleration because of gravity. And you can see how this is curved. This is because of gravity. There's no gravity or acceleration, so it's a straight line. So let's talk about the relationship between position, velocity, and acceleration with respect to time. If you know velocity, that's miles per hour, meters per second, kilometers per hour. That is a distance related to time. So meters per second is meters. Meters divided by second. That's velocity. Position is just meters, not meters per second. Just meters. Acceleration is distance divided by time squared. So, yeah, this is super important. So if you guys know anything about integrals or derivatives or areas under curves or tangents and stuff like that, or slopes, you will understand how these are all related. So we can get from one function to another to another. So let's look here at our component x displacement and y displacement. So right here we can see it increases linearly for the x displacement. So here in MATLAB, I'm going to do some runs. This is the graphical representation of this is wrong, sorry, x versus y, which is what you see on the glass. So explosion here, 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 whatever. So let's talk about, this similar graph I just showed you from Excel. This is the x linear relationship. This is the y curvilinear relationship with time. So if we take the derivative of it, because this has a constant slope, it's going to turn into a straight line, which we could see here. Here's the velocities. So the x direction, the only thing that's ever going to change when you change the guider, as in, like exposure. So if you use a slab, a full block, TNT compression, the velocity is going to change, which is the important thing. This is going to stay the same because it's only gravity present. So this is the derivative of it. If you have 12x, the derivative, it's going to remove that x, it's going to turn it to 12. If you have 2x squared, take the derivative, it's going to become 4x. But because of gravity, it's negative, it's going to go downwards. You don't need to worry too much about taking derivatives for cannons, but it kind of explains the relationship between all of them. And so that's the velocity. And then looking at the acceleration, there's no acceleration in the x direction. So when you take the derivative again, it's 0. No acceleration because of gravity. Constant acceleration. Very important. No acceleration in the x direction, constant acceleration in the y direction. That means velocity only applies here, acceleration only applies here. Really important stuff. So effectively, the only difference between a cannon that shoots 5,000 chunks in one tick and this cannon right here is the amount of main power. It's going to drop the same amount per tick because there's no y component, so the only thing happening is acceleration, which is gravity. Gravity is the same all the time, and for time I mean like everywhere. So gravity is going to work the same way on every single cannon as long as there is a guider. So we are restricting the upwards y velocity, removing that component, so there's no curves. It's just downwards. But let's talk about power. So what I have done here is I have fired the cannon on this timing using all this, then that, then that, then that, then that, then that, then that. So you can see the different explosion marks. So for example, this one here corresponds to just like all the way out here. And you can see here these bedrock marks show the explosion location, like the center of it, we'll say. And the only thing that varies here is the x direction. Keep in mind, all the explosions are happening in the exact same spot vertically. So here, I'll just demonstrate it real quick. Here it is with the full power, and I'm using a ladder for this. Sorry. All right, now let's fire it. Jumping, 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 so random errors. Explodes there. Let's take off a lot of power. So we're only going to use 3 TNT. And of course, I'll add that back for you. So normally, what would you expect? Think in your head, what would you expect to happen? All right, hopefully you have an answer. It explodes in the same y spot. So let's take a look at the graphs. Here is what I just showed you. There is slight errors present, but it's fine. The height the explosion takes place is the same in every single one of these, with a slight exception here. Here's the origin of the cannon. The only thing that changes based on the amount of TNT is the x location. So that further reinforces the point I talked about a second ago. When you remove the y component of velocity with a guider, you're strictly focusing on the x direction, which is what we want. So we can see here, the amount of TNT we use directly affects how far it shoots. Well, duh, Jared. That's obvious. That's why I have a lot of power in our cannon. But the location of it is extremely, extremely, extremely important. With all of our power, explosion happens here. Taking off the one TNT in the back, it decreases a little bit. Huh, that's weird, you begin to think. How does that happen? Taking off another piece of TNT, it's a little further, slightly. But then we see huge jumps for every piece of TNT we remove, and all of a sudden we get to this point where one TNT doesn't have that much effect. So let's figure out why. Now what I've done here, don't have a heart attack. I have now added dispensers. So we're going to move on from our shitty cannons from 2000 and late, we'll say. So what I've done here is I've fired, instead of firing it like this and then taking off from the back until we get to here, I have isolated specific spots. So I've isolated here, I've isolated here, I've isolated here, I've isolated here. So the reason why I have 3 dispensers is using only one piece of TNT, it's going to be hard to track it. So what I've done is I've used 3 TNT, and then I've divided my answers by 3, just so we can have a better resolution, a better idea what's actually going on. So, for example, let's fire this. It barely moves. Okay, so keep that in mind. Now we do that for every single location, and still slight error is present because, for example, this doesn't even hit the guider. So now we have a Y velocity component, which is going to slightly skew our results. But here are the location explosions. Location of explosions. It's pretty consistent across here. Again, slight errors. And we can once again see the relationship where further out, or the closer to the element we're shooting, the further it goes. And obviously it decreases to just dribbling out of the cannon. So we're here back to Excel, and what I've done here, this blue one, this is this basically. What I've done is, this is the width of the booster, but by taking it off. So if we use no TNT on either case, either the normal hand-placed cannon or the one with dispensers, obviously there's going to be no horizontal displacement. I know this is weird, that the X direction is this way, but we need to create some sort of relationship with the amount of TNT. So we have here, and this, if you think about it, use your brains, you guys are actually smart, it will make sense. It's just a little confusing having this here. So the width of the booster, the distance from the TNT explosion, so whatever, we have our component exploding here. This is our projectile. The distance here affects this. So if we have an explosion here, this won't go as far as if the explosion was here. So this is kind of the relationship. Let's look at the blue line. If we use all of our TNT, we're going to have maximum displacement. If we take off the one little teeny TNT in the back, it's going to decrease, and then it's going to decrease more and more and more and more. So once again, it's another, I don't want to say, it's a polynomial, quadratic, parabolic relationship with the amount of TNT. So this right here, this is the isolated graph. So you can see for each TNT, again, divided by 3, as we can see here, but with no TNT, obviously goes there. With the first one, it explodes 17 blocks. Then as we go further out, it decreases. So we could create some sort of relationship probably with what the distance from the projectile, how much the TNT affects that. I think that's out of the scope of what we're doing, because this shows us the only one we want to ever worry about is the first TNT having your propulsion as close to the main power as you want to have your main power, whatever your boosters are, we want that to be as close as possible to the object you're shooting to make it shoot the furthest. So basically any sort of booster, we want to have it as close as possible to the projectile. That is a very important idea. So to recap some of our very, very, very important ideas. First, when we're shooting something, if you're shooting a bow and arrow, if you're throwing a snowball, shooting a gun, how you shoot it is really important. So in our cases with cannons, If you want to increase the horizontal direction, we want to use a ladder to prop it up because it removes friction and it gives us an angle. And the issue is, though, if we do that, there's going to be an x component of velocity and a y component of velocity. So in the x direction, there's going to be a linear relationship. In the y direction, which is upwards, it's going to be a parabolic relationship because you would have velocity and gravity. If you use the guider, you're ignoring the y part, which is what we want, because gravity is going to act the same no matter what. So any cannon you have for a certain amount of time, be it 4 ticks, 3 ticks, 2 ticks, 1 ticks, it's going to drop the same amount based on the given time. So the only thing we want to ever worry about is the x component, how far it shoots per unit of time. Another thing we're very interested in is the location of the TNT in the cannon relative to the projectile. We want to have as much TNT as close to the projectile as possible in order to maximize the horizontal distance it travels. The y distance, no matter where you put your thing, it's going to be the same, because with a guider at least, because gravity is going to act the same on every single case. We want to have all the TNT closest to the projectile to increase the horizontal distance traveled per unit of time. I hope this was informative and talk about things no one else has talked about. Keep in mind, all this is interpreted by the Minecraft engine, which maybe I'll talk about it in the future. I think the next video I will do, I'm going to talk about actual history of cannoning. So kind of start off with these derpy little cannons. We're going to go to then the first hybrid cannon. Then we'll go to like cobweb cannons where you just throw sand at a wall. Then we're going to talk about the lane cannon, and then basically everything up to now. So I think that'll be the next video. Please give me like comments on the presentation of this, whatever, for those few that are going to pay the however much to watch this. I had a lot of ideas I wanted to talk about, and it kind of just went out the window because me doing streamer conscious videos, yeah. Cool. Thanks for stopping by.